All right. Well, let's talk about reactive programming. And I want to start out by asking the question, is this something totally new? Well, we work in a field where right about every 10 years or so, we'll give a new name for what we already do and get really excited about it. This time around, we call it reactive programming. Things like microservices and stuff like that are getting the excitements. But one of the reasons for really having something that's been around is, in a way, reactive programming is kind of like extreme programming. If you recollect, extreme programming had really nothing new in it, except for the emphasis it brought together 12 principles we have to really focus on. In a similar way, reactive programming has nothing new in it, except it brings 4 different things together with a greater emphasis. And so the question is, what's the reason for this? So it's really a lot of old concerns with a little renewed urgency and energy put into it. But why is this different? Well, a few reasons. If you look around for the past about 10 years, maybe 15 if you push it, we are doing a few things very different than we used to do. One of them is big data. We're talking about high volume, high frequency of data that we are working with. And a lot of organizations are working with data that is in a proportion or disproportion to what we are used to in the past decades. The second thing is the internet has changed a lot of things. I'm almost in tears when I say, when I think of my time decades ago, when in the morning I used to wake up and, as the coffee pot is brewing coffee, I would turn on my modem and I can hear that whoosh in my ears. It would connect and reconnect. I can call my friends and ask them, what's the baud rate you're getting today? Well, those days are gone now. Every one of us is carrying multiple internet-enabled devices with us, and we are constantly communicating with applications and transmitting data. The biggest geek that I know personally is my son. The other day, I patted him, and several devices fell off him. I don't even know how many he is carrying these days. And we're talking about other ways of communication as well. Very soon, forget about watches. We're talking about earrings, nose rings, and tongue rings, all internet-enabled. And we're not far from a day when you may get a call from the doctor's office that says, sit down, we are measuring a very high blood pressure level. And you can just tell the doctor, no, don't worry, I'm just listening to Venkat talking. That usually does it to me when I listen to him. And the point really is that you can, monitor health, and you can monitor devices, you can monitor appliances, you can monitor several things constantly. And we are living in this world of internet-enabled devices. And the usage patterns have changed a lot as well. Well, one of the key distinctions is, only about 10, 15 years ago, we had companies making applications for their employees to use, and then they made their employees available to their customers. Well, employees using applications, they're called captive users. Nobody cares what they think about it usually. But on the other hand, when you make applications for end users to use, end users are not that kind. We demand a lot more from applications, and also there's a very, very high volume of users when users use directly applications than employees use applications. So to manage these things, we are rethinking about how applications can be developed, and this is where reactive applications come in. So what is it really? Well, reactive programming was created in the Microsoft world. Eric Meyer introduced this idea a long time ago, but this is not really that new. In fact, you can even trace back reactiveness to maybe 40, 50 years ago. I'll give you a couple of different examples of reactive applications, even beyond when we call them as reactive. One of the probably the most known reactive applications out there is Microsoft Excel. Phenomenal tool if you really think about it. Well, in Microsoft Excel, you could have thousands and thousands of cells, and you could modify a cell over here, and before you could blink your eyes, several of them could be modified based on the change you just made. That's reactive, for example. One of my aha moments coming in touch with reactive applications is Google Docs. I travel a lot worldwide. I'm in different parts of the world all the time. So I live in a more of a nomadic digital life. And a lot of times the way I can communicate with my wife is through electronic medium. So my wife and I share a Google Doc where we constantly update things we have to communicate about. But there was one thing I realized one morning that just changed the way I look at it. I got up one morning in a different part of the world, and I noticed when I went to Google Doc, I noticed at that very instant, my wife was using the Google Doc as well. And this was phenomenal discovery for me because I realized that I could actually exactly click the mouse at the point where she is editing, and I could edit at exactly the same time. This gave me the way to realize you could be thousands of miles away and still annoy your spouse. That's a phenomenal application of reactive programming right there. So these applications give you the ability to communicate across the globe, and you're able to exchange these ideas really well and interact with applications. And what is really part of this? Well, obviously, in this case, one of the key things here is responsiveness. And responsiveness is where multiple people can collaborate simultaneously with documents. That is reactive. Not only that, as data changes that can immediately respond to in the application, that is responsiveness as well. So what it really amounts to is these 4 different pieces put together. The first is reactive applications are message-driven. It is so 20th century to think about a centralized database with distributed transactions. If you are going to build serious applications in the modern world, we want to be able to communicate between different disparate parts of the application using messaging. Well, messaging, again, is nothing new, but reactive programming greatly emphasizes the fact that we should be using message-driven technologies. The second thing is elasticity. It is really, really hard to imagine organizations in today's world maintaining a huge amount of staff to maintain their infrastructure. Well, I was talking to a client recently, and I asked them on a given day how many users use your systems, and they said, well, about 200 people use the system. I was kind of like, wow, you guys are making billions of dollars, only 200 users use your system. No, on a given day, only 200 people use it, but on 2 days of a month, about 50 million people use it. How do you scale between about 100 people using your system on a given day to several millions of people using your applications on just a few hours in a month? Well, clearly we have learned a great lesson from this, from cloud computing and the infrastructures of the cloud. Elastic computing is something we have benefited greatly from. Well, with elasticity, you could either be dynamic or you could program ahead of the time. When your demand goes up, you could have more servers come to life. When the demand goes down, when people are using it less, you can turn off those servers. You're not expending money on those systems. So elasticity is something we have really learned quite a bit over the years. And reactive applications engage elasticity to scale, and that is another thing it really emphasizes. And I mentioned about responsiveness. Responsiveness is probably a very important thing to consider. If your application it could be the best application in the world, but when a user comes to your application, if it doesn't respond properly, you're going to lose users very quickly. And in today's world, the applications that are going to lose users are not applications that are not useful, but it's the applications that are not responsive, however useful they may be. For example, let's say you walk into a store on a Saturday morning and you see that this clerk is busy helping somebody. So what do you normally do? You probably look around for a few minutes, look at the wall, look at the ceiling, look at the floor, and you quietly walk away because there was no response. On the other hand, you walk into the store, the clerk who is busy makes an eye contact at you and says, I'll be with you shortly, and then continues to help the other person that they have been helping with. You probably spend a good 10 to 15 minutes in the store waiting. Why did you do it? Because you felt important even though you know you're not. And the point really is that when there is responsiveness, you have the loyalty of the user hooked onto it. That's one of the biggest differences. So responsiveness is extremely important. Well, talking about responsiveness, remember the day you discovered the infinite scroll feature? You've been using this app for a while, but then you walked into this application, use the application, and then you scroll down. Today it was a little faster, but as you scroll down, there's nothing in the bottom. Before you realize it filled up with data, and then you scroll again, and then it fills up with data, and then you realize, oh, wait, I don't have to be loading up all the data right now. I could be getting data, and as the user is looking at the data, there could be more data being fetched at the same time. That's, again, an example of how applications can be responsive. Infinite scrolling becomes an example of that. The fourth component of reactive programming is resilience. Now, I could ask you, how many applications do you have on your smart devices? You probably have hundreds of applications on your smart device. I may ask you how many you normally use. You probably use about a dozen of them regularly. What about the other applications that you don't use at all, but they are still installed? Well, they are pure crap. You have used them a few times. They don't behave very well at all. In fact, you got so angry, you left the application there to die. They don't even deserve you to click on them to delete it. That's how you feel about applications that are not working properly. Resilience is extremely important. Well, this brings back some sad memory, actually. I was speaking in one of these conferences. I've been teaching at the university for about 30 years now. I was speaking in one of these conferences a couple of years ago, and one of my students came to me, or one of the attendees came to me and said, "Oh, Venkat, I took your distributed object computing course back in 1998. I said, "Oh my gosh, I remember teaching that course way back in the 90s. He said, "I got a story to tell you." I said, "Oh, I love stories. Tell me a story." He said, "Well, I was in your distributed object computing course, and I was in the middle of a final demo of the project. And as I was demoing the project, you walked up to my machine, quietly disconnected the internet cable, went back and sat down and said, 'Continue,' and my project miserably failed, and I failed the course." I said, "I'm really sorry. Why would you want to tell me a story like that where you failed?" He said, no, there's a good news after this. I said, "How could a good news come out of a failure like that?" He said, "Because that's the last day I ever made that mistake. I programmed only for the happy path. I did not think of network failure, but you taught me a really important lesson about resilience. Now when I code, I don't program the happy path first. I program all these error conditions very well." He went on to say that his programming has changed ever since he failed that course, because he went on to say that today when he codes in his office, as he's writing applications, in front of him on the wall, there's a picture of evil Venkat that he looks at. And then when he looks at this picture, he knows he has to code the errors as well properly. I don't think anyone wants to have a picture of evil Venkat in front of them to code resilience, but it's important for us to really code for resilience as well. That becomes a very important feature to consider. So given these 4 features, can't we just program this using what we already do, what we already have? Well, let's talk about multi-threading. Well, what do you do in multi-threading? You create threads, and then the fun starts after that. We're not able to deal with shared mutability really well, and then all these synchronization primitives really make the application very complex, and we're not really doing very well at all with it. Well, okay, maybe we should use futures. Well, what do you do when you use a future? Well, you call a method which is going to run something asynchronously or in a different thread, and what does that do? It immediately gives you a future back. You get a future, what do? You normally call a get on the future. And what happens when you call get on a future? Well, your thread gets blocked. That's no future at all. That kind of sucks. So that doesn't really give us a good solution. Hey, but wait a minute. We could really do asynchronous communication and handling by using callbacks. If you think callbacks are a good idea, here's a suggestion I have for you. Just walk up quietly next to a JavaScript programmer and the word callback, and then just watch them begin to cry unconsolably because they know that callbacks really suck. Callbacks don't compose really well. In fact, the JavaScript world has moved away from callbacks into promises mostly, and the equivalent of promises, if you want to really say it's equivalent, is something like a completable future in Java. So we are moving away from those directions as well. But what is it really that we are looking for? One of the key things I want to emphasize is that efficiency is attained not by doing tasks faster, but by avoiding tasks that shouldn't be done in the first place. So the real efficiency is not to really program our way to running things quickly, because at some point the volume is so big, we cannot just compete by speed alone. We got to be smarter than that. And so the question is, can we be lazy about evaluating things? And understanding this particular idea was a big change in my mind. And one of the things to tie this back into is, I was trying to put together what does reactive programming really mean in this context, and a little light bulb went in my head when I realized that functional programming actually has 2 interesting ideas. It has function composition and lazy evaluation, and I realized that reactive programming is a nice logical step from functional programming. Functional programming gives us composition of functions and laziness. It says you can evaluate a series of operations now, or you can postpone evaluating them until a later time. reactive programming takes that idea and runs with it. So I see reactive programming as a very nice logical extension to the ideas espoused by functional programming. But one of the key things here in terms of resilience as well is to really respect failures. So in other words, we treat errors as first-class citizens. So rather than treating error as something that is unnatural, we will be treating errors like it's something that's normal and that can happen along the way, and we deal with it like we deal with data as well, and that's basically what it provides for us. Well, okay, so what does this really mean from the point of view of programming it? Well, before we talk about it, let's really talk about something a little bit different. What have we been doing for the past about maybe 15 to 20 years? Most of the applications we've been developing could be put into this one acronym called the CRUD applications. Now, we've been developing CRUD applications pretty extensively. We've been doing creating data, reading data, updating data, and occasionally deleting data. But at one point, we wake up and ask the question, is everything a CRUD application, or have we gone overboard with it? And it turns out, maybe there are applications that don't quite fit into the CRUD model. Maybe it's not all about reading data from a database. It's not all about updating data into a database. What if I were to think of applications that are very different than what we used to create? For example, what if I'm interested in monitoring tweets? There are organizations that are developing applications where they are listening to tweets and they are trying to infer from the tweets and looking for favorable tweets versus unfavorable tweets, and then they do some actions based on the tweets they receive. It could be a processing of things from the social media. It could be a processing of the stock market data. The stock market is fluctuating all the time, and as the stock data is changing, maybe you want to issue a trade request when the price is to a favorable value, or you may want to sell it when a value is certain things. In all these different examples, you could be monitoring a flight as it is in motion, and you are getting all kinds of data from the flight, and you are monitoring the flight status. All of these don't fall squarely into the CRUD way of programming, but instead, we should rethink about what this kind of model is, and we are talking about data flow computing. All of a sudden, it changes the way we think about applications. So what if we are thinking about data flow computing? In data flow computing, we have data that flows from a stream, and there could be any number of data or unknown flowing towards us, and as the data is moving towards us, we might be interested in taking the data, doing some operations with it, filtering, transforming. And then if it's of interest, we take a certain action, we pass it down to an intermediary or the next one downstream. If it is not interesting, we could simply throw it away. So if we're thinking about data flow computing, how does it change the way we would develop applications? Well, in the programming model, if you look at object-oriented programming, it doesn't matter what programming language you program in. We can all agree that if you're doing OO programming, you're going to see classes and objects as the building blocks of your application. In a similar way, in reactive programming, the underlying principle or the construct you're going to work with is called an observable. So what is an observable? An observable is pretty much a data flow. So an observable is a flow of data. You may wonder, how does observable differ from Java 8 streams? There are some very clear similarities and differences. Java 8 streams is a flow of data, much like observable is a flow of data. Java 8 streams can give you either a fixed number of data, or they could give you an infinite number of data flowing towards you. Likewise, observable may give you a fixed number of data, or an infinite number of data, or unknown number of data. Well, that's where the similarity ends. When it comes to us Java 8 streams, it doesn't really handle certain things for you. For example, how does the stream deal with exceptions? Well, the short answer is it handles it with two words called good luck. So it doesn't really provide you a solution for it. If you are in the middle of a stream, like a filter and a map and a reduce, if one of your lambdas blows up with a runtime exception, it's really hard to know what's going to happen if you're on a parallel stream versus a sequential operation. And the reason why this is really not a good solution is the exception handling is completely orthogonal to the functional style of programming way of thinking. The exception handling ideas are very much in tune with imperative style of programming. In functional style of programming, you deal with everything from upstream to downstream. So as you are going downstream and processing, if something were to go wrong here, you don't blow up. You simply keep going downstream and handle the error downstream. Well, Java 8 Stream doesn't handle that at all. And that's one of the biggest challenges. Second is, how do you know when there is no more data? Well, Java 8 Stream has no way to clearly tell you those details. Observable differs in some very clear manner. Well, the very first thing is, an observable has 3 channels. The first channel is a data channel, and through the data channel comes the data. So an observable will be transmitting data through a data channel, and as the data is being sent by the observable, you're going to have the data flow through the pipe transformation through the data channel. An observable also has a separate error channel as well, through which an error would flow. So it clearly gives you different channels. So it's kind of like I have a data channel through which I'm going to send data, but I'm going to have an error channel through which I'll send error. So I got 2 distinct channels through which I'll send the data. But in addition to this, an observable also has a 3rd channel, which is called the complete channel. And as you would imagine, from the complete channel, you would get a complete signal. This is a way for the observable to tell you, I don't have any more data for you. I am done. You can do the cleanup on your side. You will expect no more data coming from me. Well, the way an observable is modeled is, a data channel may transmit through the data channel 0 or more pieces of data, but only as long as there has not been an error and there has not been a complete signal. But the minute something goes wrong, an error goes through an error channel, and you are guaranteed there will never be data coming through a data channel. So in other words, a data channel is open, a data keeps flowing through the data channel, but something goes wrong, it sends you an error through the error channel and immediately closes up the data channel, so you clearly know that you got an error and there will be no more data. Well, other thing is, it doesn't throw the error as an exception at you. I mean, how rude something is thrown at you. It's very civil. It gives you an error just like it gives you a data. So the error comes through the error channel, so you can receive the error and deal with it on your side, much like you would receive the data. So this is where the error is treated as a first-class citizen. Just like data comes through, error is just a different form of data. It's an error data. Well, likewise, the minute something is done, the observable can send you a complete signal to tell you, I am done, I'm not going to send you any more data. And the minute a complete signal is sent by an observable, the data channel closes again as well. So these are the 3 channels that observable contains very explicitly for communicating these 3 things. So an observable will push the data to you, unlike a regular iterator where you pull the data. There is an end signal that's being sent to you. It respectfully deals with errors by sending the error to you in the error channel. And there is one other big benefit that you get out of this. Now, what do we normally do when we write applications? We always care about performance. But to care about performance, how do we improve speed of certain things in our applications? One way to improve speed is to use multi-threading. But something has happened until this point in our programming lives, and that is the structure of a sequential code is very different from the structure of concurrent code. And this has been a cause for disaster in what we do. So if you write an application sequentially, and then one fine day you come to work and declare you're going to use multi-threading, that day becomes the day of disaster. Because your code structure turns into a monster. It doesn't look the same anymore. But not only are you changing your code so drastically, the part of the code that uses your code has to change as well. And you're not going to invite friends by doing this. So what did we learn so far? If you start programming sequentially, it's easy to program. And you program sequentially for most part of the application, and in the end you realize performance is not good, you change your code to concurrency, and the code becomes unmaintainable in the end. Then you realize, gosh, this is not going to help. We cannot change it so drastically in the end. So in the next project, what do? You learned your lessons, you take it forward, you start using multi-threading from day one. Now your application becomes unmaintainable from the beginning itself. That is no fun either. So how do we really develop an application that actually works and come back and improve performance? Well, here's the good news. Both in Java 8 streams, we have learned this, and in reactive programming, the first time after a long time, the structure of your code is exactly the same, whether you're sequential or whether you're asynchronous. And this is the big benefit, because I can write this sequentially today, and if performance is adequate, I can keep it sequential for the full time, or if I realize the performance needs to be changed, I can make it asynchronous later on. Because the code structure is exactly the same, I can easily interject the performance improvement without having to change the code structure, and this is a huge benefit. So that's another big benefit we get out of this style of programming with observable. Well, enough talking, let's look at some examples of this. So what I want to do is to create an example, but when creating this example, I also want to get a feel for how we are doing things today, and maybe how we can do this a little different. So to understand this, I'm going to query for some data. But before I do this, just to make it a little bit more easy to understand and illustrate, I need one volunteer with a smartphone. Anyone in the audience who is willing to help me? Somebody, don't be shy. One with a smartphone, who wants to help? Come on. You can help. Who has a smartphone here? Nobody wants to raise the hand. Would you like to help? Oh, there you go. Thank you, sir. What's your name? Chris, give a hand for Chris. Thank you, Chris. Awesome. Come on up. Thank you, Chris. So, Chris, I want your help.
Sure.
I want you to find me the stock price for Apple, Google, Microsoft, and Intel. So, are you done, Chris?
Nope.
It's not done. Anyone thinks Chris is slow? Chris is very slow. What do you have, Chris, for us so far?
Loading.
Loading.
Okay, I got it.
What do you have?
One for 5 for AAPL.
You took all this time and you only have price for Apple.
Yeah, sure.
You're very disappointing, Chris. Good, Chris. Well, Chris is demonstrating some really good ideas right now. He is looking for the next prize. What do you think of his performance? Just like web, isn't it? Thank you, Chris. You demonstrated very well.
Thank you.
So, thank you.
I got another one.
Yeah, he has another one. So, Chris demonstrated a few things really well. I couldn't have done it better than he did. He did a few things really well. The first thing he did is, when he got the request, what did he do? He started really going through and finding the data for all the 4. And as he was doing it, what did I do? I was not so nice. I kept interrupting him. So this is typical, right? You go to a website, and you see that the website is very slow. So what do you do when the website is slow? You're saying, gosh, this website is slow. Let me help it. And you hit the refresh button. And what happens when you hit the refresh button? There is 2 threads running now, not 1. That's exactly what I did to poor Chris. When he was trying to find the stock price, I kept annoying him with more questions. He had to create more threads to answer me while he was still looking for it. That's exactly what happened. And then, of course, he took the job upon himself to find all the prices. In the meantime, I made signs he never noticed. I said, this timeout. I said, don't do this. He did not notice anything at all, just like a typical web application. What do web applications do? Hey, user, you have a request, and goes around and works on it and says, result, where did the user go? And it doesn't really know. The user doesn't care about the result anymore. And this is exactly how web applications work. He did really well. And I've done this talk a few times, and one of these times I had somebody like Chris come up on stage and help me, but that person, Rick, did something very different. I've never seen anyone do this before. I've never seen anyone do this after. What he did was kind of unusual. When I gave him these 4 stock prices, rather than going and finding these stock prices, Rick immediately turned around and recruited 4 people. And he said, hey, you find the price for Microsoft, you find the price for Intel, you find the price for Google. And by doing so, Rick demonstrated not only can a system suck, a cluster of machines can suck as well. And that is just amazing how we doing this for a long time, and so we have to fundamentally rethink about the way we build applications. So thank you for the help over there. That's kind of the way we've been building apps, but let's see how we can do this a little different. So what I want to do a little differently here in this case is that I want to go ahead and say, well, go ahead and bring up a stock a server.getFeed, and I'm going to pass to it the symbols that I'm going to provide for it. Well, what does this do? There's a getFeed function I'm going to create, and the getFeed is going to return a feed for me. And let's kind of entertain this a little further and see how this is going to work. So in this case, what I'm going to do here is I'm going to ask it to go to the feed, and in this case, let's go ahead and implement that little method I'm interested in implementing. So in this case, here's the getFeed method. Well, we need some tools to implement this. There are several tools available for this. I mentioned that Microsoft Research introduced this idea years ago, and I program with C#, I program with the Microsoft languages and tools, but I've noticed one thing very different between the Microsoft world and the Java and JavaScript world. In the Microsoft world, if you introduce a solution, they will quietly sit there and use it and produce value. So this has been in Microsoft world for a long time. Nobody really talked about it. But there's one thing very different from the Java and JavaScript world. When you go to the Java and JavaScript world, you show a solution, people don't use it. They immediately get excited about it and create 20,000 framework around it. And that's where people got excited about this. The minute the Java and JavaScript world came to know about this, there are so many solutions. There are several solutions in the Java world now. There are solutions in the JavaScript world too. In fact, this has been a really aha moment for me. I've been looking at reactive programming for a few years now. I tell you, in the last about maybe year and a half or so, almost any tool and any library and framework I'm using suddenly has turned into reactive. For example, Spring 5 is reactive, as they say. There are so many other tools that are reactive as well. You cannot escape reactive programming moving forward. A lot of different tools and libraries are already using this. So in that regard, I'm going to go ahead and use one tool here. So I'm going to say observable, and in this case, observable of stock info. But where in the world is this observable coming from? Well, this observable in this case is going to come from the RxJava. Well, RxJava is a tool created by Netflix. Apparently, they have some streaming issues to deal with, so they decided to open source this tool. You don't have to use RxJava. There are other tools like Vertex you could use as well. There is Akka, also is a reactive library. There are so many solutions available on the JVM today. But this is just one example, and RxJava does a fairly good job as well. So in this case, I have observable I'm going to return from here. But what I'm going to do here is I'm going to simply say, let's go ahead and say created observable. And then how do I create the observable? Well, I'm going to say observable dot create. And this uses the same principle in effective Java. Rather than using a constructor, use a static factory method to create it. And I'm going to say, in this case, embed. Let's call this as emitter. And what I'm going to do here is I'm going to emit data to the emitter, and I'm going to pass the symbols to it. Let's go ahead and implement the emitter method right here. So what is the emit method going to do? Well, it receives the emitter and the symbols. And I'm going to go ahead and say, in this case, start emitting. Well, and the point I wanted to make is the following. So I'm going to go back over here to this sample over here, and I'm going to go ahead and save this away into a variable called feed. And then once I save it into feed, I'm going to go ahead and say got observable. Now remember, one of the things I said, efficiency is attained not by doing things faster, but by avoiding things that shouldn't be done in the first place. So when I go ahead and execute this little example here, what it actually does in this case is it says created observable, and it says got observable, but quite important note is it did not start emitting. And the reason it did not start emitting is it's pretty darn lazy. It says, look, you haven't really used the data, you haven't started using the data yet, so why should I bother really doing anything? So it's pretty lazy, as you can see. Well, what I'm going to do now is I'm going to go to the feed and say subscribe, and now I am subscribing to the data that's going to come from it. Well, remember from our discussion a few minutes ago, an observable has 3 different channels. It's got the data channel, the error channel, and the complete channel. Where are those 3 channels? Well, those 3 channels are going to appear here as 3 functions we're going to pass to the subscribe. So the subscribe already has 3 channels you can subscribe to. So in this case, I'm going to say data coming from the data channel. I'm going to simply output the data. And you can write it this way, definitely fine. Or you can say, given an error, I can simply output the error. And as we know, we could also write this as system.out. And then, of course, we could simply say println. And this shows you the 2 different ways to write it. This is the data channel. You could have written this like this also using method reference. This is the error channel. You could have also written this using the lambda like this also. And finally comes the complete channel. So in this case, I'm going to simply output. Let's go ahead and say done to say that I'm done. I don't have any more data. Now when I go back and run this, you can see in this case it says start emitting. And the reason, of course, is because we did subscribe to it and it can no longer be lazy. It says, oh, you are really interested in the data I'm going to send. I might as well start emitting to you. And that's the subscription that's going to start. But of course, I really want to get some data through here. So what am I going to do? I'm going to go back to the service right here. And instead of saying start emitting, what I want to do here is to really do the emitting. So I'm going to say while, let's go ahead and say in this case, count is less than, let's say 10. Let's go ahead and say count is equal to 0. And in this case, of course, while count is plus is less than 10, I'm going to start emitting some data. Well, the way I'm going to emit it is, I'm going to say symbols.stream, and then I will go ahead and say .map. And in this case, given the symbol, I'm going to say stock info, and I'm going to call a fetch method. Well, the fetch method is going to take a symbol and return the stock info object for me. And the stock info contains the price of the stock and the ticker symbol. And then I'll say for each. And then I can say in this case, you have a stock info given. And I'm going to say emitter dot, and I will say on next. And then I will send the stock info to it. Or as we know it, rather than writing it this way, we could write this as simply using a method reference. We could say emitter on next as well, and then we could just pass that through. So what's happening in this case is I am receiving the data, the symbols, I'm converting, transforming it to the data, and the minute I get the data for the stock symbol, I'm going to go ahead and send it across to the emitter. Well, this is the mouth of the data channel where we're going to start emitting the data going through it. So as a result, now when we go back and run this little code, what we're going to see here is that it's going to start emitting data from the service. And right there is the Apple stock price and the Google price and Microsoft price. Just it's fetching the data from the fetch method and giving us the data as it goes through. And I've asked it to send it 10 times, and it's sending it as many times as I asked for. So that is an example of how this can be transmitted to us as it goes on. I just stopped it. So you can see how that's going to be transmitted to us. So this is where the emitting is happening. And of course, in this case, we can see that as the emitting is happening, this is on the receiving end and it's displaying the data. Well, this shows us how we are able to receive the data. But one of the really cool things about the observable pattern, observable abstraction here is it is a stream of data. So you have an observable that's going to emit the data, and I'm the subscriber interested in receiving the data and handling it. But there are times when you may have intermediaries that want to do certain things. For example, let's say you are not interested in any price that is less than, let's say, $100. Well, here you can see there is some price less than 100, some prices more than 100 as well. But what if you're not interested in any price less than 100? Well, the beauty of this is you can put these intermediate operations. These are subjects. Subjects can become observable, subscribers to upstream, and they become observables to downstream. So I can be in the middle and I can say, I want to only transmit data that's meeting my selection criteria. So you can see the functional programming concepts emerge really well right here. I can say stock info dot value is greater than 100, and otherwise don't bother transmitting it. So now when I run this code, you can see, in this case, you can see Apple, and you can then see Google come through, but you don't see Microsoft and Intel because the values are less than $100. So that gives you an idea about how this can be filtered out. Similarly, you can perform a transformation. You could say .map, and then you could say return a new stock info with the stock info ticker, and then maybe I can take the price given to me and maybe add a commission to it and say 1.1. And this is going to transform the data and send it along the way. And you can see the price is inflated right now, as you can see in this particular case. So the point really is, you can have these beautiful set of observables that can transform the data along the way, and you can do operations with it. So what this tells us is, you could start laying down this pipeline of operations. Data could be emerging from a data source. There could be a subscriber on the tail end, but you can start putting any number of levels of intermediate operations that can go through, and as the data is being emitted, it can process that. But on the other hand, like this particular thing, something could go wrong and things can start falling apart. What do you do in that case? Well, to illustrate that little point, let's go back to this code for a second. And notice in this case, I'm transforming the data and simply sending it. That's all I'm doing. So when I go back and run this, you can see it's reporting the data as it comes through for Apple and so on. But what if something were to go wrong? What are we going to do about it? Well, to illustrate this point, let's go to the fetch method right here. And in the fetch method, I'm going to simply, right in the middle of this with nothing else, I'm going to simply put a random is less than 0.2, I'm going to blow up with a very useful message called oops, ran into trouble. So in this case, it just blows up, as you can see. But we talked about this earlier. Blowing up with exceptions is a terrible thing to do, because exception is an imperative style of programming concept. It doesn't jive well with functional style. So what do we want to do? When something goes wrong, what you really want to do is you want to capture exception, and then you want to deliver that as like a data, but you want to deliver that as an error rather than as a data. So in other words, this exception that's happening here should be transferred through an error channel, and the data channel should close up at this point. Let's see if that's going to happen. So I'm going to uncomment that random is less than 2. Let's go back here and run the code right now. And as you can see right here, as it is getting the data is arriving for Apple, Google, Microsoft, and so on. But at any time that particular thing is going to blow up, what is it going to do? Well, it's going to capture that error, but it's going to send it to us here as oops, ran into trouble. And notice that got printed right here. In fact, to make it really clear, that's what really happened. If I take the error right here, and I'm going to say, error here, and then I will go ahead and say colon and plus error, so that way we can be sure that we really are receiving that here on this end. So that exception that occurred on the other side has been captured by the observable, and it transmits to us as error through the error channel right here. And then, of course, the data channel closes up. We don't get any more data from it. And so the error becomes data, like error becomes a first-class citizen, like its data, it's handed to us separately. So you can be working with a system where something could go wrong. Now, of course, the question is, when error happens, why are you not getting any more data? Well, the reason simply is it's based on the concept of circuit breakers. If something were to go wrong, you don't keep pinging for more things from it. You let it heal. Well, one of the things you could potentially do here is, depending on your application, you could say on error resume next, and you could switch over to an alternative or a backup service if there was an error. For example, if I'm looking at, let's say, one map, let's say Google Map, and something was wrong, I don't want to say, gosh, I don't want to go to where I want to go today because the map is broken. Well, dude, go use some other map to get where you want to go. So I may switch over to a different map at that point. That's the whole point about this is you can switch in the case of an error to a backup service, and you could do that as well if that makes sense to what you want to do. So what we saw right now here is we looked at observable as a stream of data. Well, one of the beautiful things here is you can unsubscribe from this as well. So you can see in this case, we saw how the error was handled. There are several other things you can do with it. One of them is you can unsubscribe and say, hey, thanks, but no thanks. I don't want you to give me any more data. And you can unsubscribe from the observable as well. And you can send a message by calling a dispose on the observable. And so the observer can then know it is not going to send any more data to you. Likewise, as I mentioned earlier, your observable can also send a piece of data to the client saying, well, let's take a look at this really quickly. I'm going to say emitter.onNext new stock info. And in this case, I'm going to simply send blah and 0.0. Just to illustrate a silly example here, if I go back over here, let's make this less than 3. So if you notice in this example, when I run this, you can see that it goes through and gets the prices for us and prints those prices, but then at the very end, it's going to get the blah, which is the last value that I'm sending out. But what I'm going to do here is, right before this point, I'm going to say emitter.onComplete. I'm going to send a complete signal. Well, notice there's the blah coming through because I've not set the complete yet. I just made the change to the code. But this time when I run this, though, notice that because I have completed this and sent a complete signal, it no longer will send the data through the data channel because the data channel closes up. So as a result, you can see in the very end, it displays the done that is right here and shows that it's done. There's not going to be any more data coming through. And of course, the blah did not come through. That is the data channel shutting down when the complete signal has been sent, and that's already programmed in it. Likewise, you can do things like skip, take, and evaluate. I used a filter. Filter is kind of like a valve that opens and closes per data. But a take while and skip are like, for example, they would permanently be closed after a certain point, or they can stay closed in the beginning and open up when a certain condition is met. You could do that. And last thing about asynchrony, how do we handle that? Well, one of the beautiful things about this is, if you ever want to run this in asynchronous mode, all you would have to do is come in here and say subscribe on, and you can say schedulers, and you can specify what kind of thread pool you are interested in. If your job is predominantly computation intensive, you can use a computation pool, which will create as many threads as the number of cores. Or you can also create, for example, an I/O where it'll keep creating threads as the requests are coming in if threads are not available in the pool. But the beauty of this is the stream processing can now be asynchronously in multiple threads rather than having to be done in a single thread. And you can see the structure of the code is not very different. You are able to just interject that request for running in asynchrony very easily. So to summarize what we talked about so far, we can use these kind of facilities very easily to rethink about how we build applications. Predominantly, we've been working with applications that are CRUD modeled, but we are beginning to rethink about data flow computing. Data flow computing has been around for a very long time. It's not new, but the idea has lingered around for a long time, but usage of it has been kind of iffy over the years. But it's a resurgence of the data flow computing. There is a data source that wants to keep transmitting data to you, and you want to be able to handle this data as and when the data becomes available. You want to be able to use the efficiency by being lazy, and you want data to be pushed towards you, but only when you're interested in the data. And then, of course, the error handling has to be done fairly well. So to re-summarize the 4 key principles of reactive programming, you want the application to benefit from message-driven systems. You want this to be scalable through elasticity. You want to handle resilience, deal with the data and error properly, and you want the application to be responsive as well. And there are 2 places where you may begin to use. your own libraries and APIs, you may begin to use reactive programming and reactive solutions. That's one aspect, but the other one that you cannot probably miss out is the libraries and frameworks you use. A lot of them are already beginning to change into reactive APIs, and this is something we cannot escape in the long run. So learning about reactive programming and applying it is something that I think is going to benefit us in the long run. And besides, it's also, like I mentioned, seems like a very nice logical step to where functional programming took us to. It takes us right from there and turns the lazy evaluation and function composition into something very practical. Hope that was useful. Thank you.